Hi folks, this is Linear Algebra Checkpoint Quiz 3. We're given a new definition to play with. Given two matrices, n by n matrices, A and B, we say A is similar to B if there's some matrix P so that A equals P inverse BP. If A is similar to B, we write that using this notation. Okay? So, the first thing I have to show is I have to prove if A is similar to B, then B is similar to A. So this is what's called a conditional statement in mathematics. This is called the hypothesis, the if part, and this is called the conclusion, the then part. And one method to prove a conditional statement is to assume the hypothesis. So we're going to assume A is similar to B. That means that it's our job to show B is similar to A. So that's what we're trying to do. That's the overall schematic of this proof. So let's do that. Let's assume A is similar to B. What's that mean? Well, by definition, there's some matrix P so that this happens. And there's a matrix P so that A equals P inverse BP. Now I go back over here. What am I trying to show? I'm trying to show B is similar to A. Well, what's that mean? I go back to my definition. If I want to show that B is similar to A, then there is a matrix. I don't want to call it P because P is already being used. I'll just call it M so that B equals M inverse AM. So I'm just applying the definition to this new case. So I need to show, so I need to find a matrix M so that B is M inverse AM. So how can I do that? Well, I can start messing around with this equation. Essentially what I can do is solve this equation for the matrix B. So how do I do that? I'm going to multiply both sides on the left by the matrix P. So I'm trying to solve for B. So I'll multiply both sides on the left by P. Now I can use associativity of matrix multiplication . P times P inverse is the identity. And the identity times anything is that thing. Now what I can do is multiply on the right both sides by P inverse. So once again, I'm solving for B because that's what I need to do. I got to solve for B in terms of A. And using associativity again, and I get the identity again. So B times I is B, and so I get B is equal to PA P inverse. Now at first you might be a little disappointed because I'm trying to find a matrix M so that B is equal to M inverse AM. Well, I can match this up. I can let M be P inverse. Okay, so we're at this stage. We're going to let M be P inverse. Then M inverse is P inverse inverse. And as we talked about in class, P inverse inverse is just P again. So I'm calling this guy M. And we've just shown that this guy is M inverse. So hence, there's a matrix B, or there is a matrix M, so that B is M inverse AM. In other words, B is similar to A. So that proves then number 1. Okay, number 2, we're asked to show that if A and B are invertible, and A is similar to B, then A inverse is similar to B inverse. So if A and B are invertible, in other words, A inverse and B inverse exist, and A is similar to B, then A inverse is similar to B inverse. So what's our little schematic here? We're going to do another direct proof. We're going to assume the if part. So we're assuming two things. One, A and B are invertible. And two, A is similar to B. What do I have to show? I have to show that A inverse is similar to B inverse. So that is, there is a matrix M, so that A inverse is equal to M inverse B inverse M. Okay, so that's the outline here. So assume A and B are invertible, and A is similar to B. There exists a matrix M, matrix P, using my definition there, so that A equals P inverse BP. Now I have to somehow get A inverse and B inverse here. Well, how do I do that? Well, I'll just take the inverse of both sides. How do I know I can do that? I'm assuming A and B are invertible, and P has to be invertible to even talk about P inverse. So what I have on the left-hand side is an invertible matrix, and on the right-hand side I have a product of 3 invertible matrices. So I'll take the inverse of both sides. And once again, P, B, and P inverse are all invertible. And the way you take the inverse of a product is you take the product of the inverses in the opposite order. So this will be P inverse, B inverse, times P inverse inverse. And as we just mentioned, the inverse of an inverse is the matrix itself. So I get A inverse is P inverse, B inverse P. So guess what matrix ends up doing the job? My original matrix, P. So by definition, A inverse is similar to B inverse. So that'll do it then for the second claim.